Let's talk about some periodic trends in the periodic table. So first of all, we're going to be talking about atomic radius. Atomic radius essentially is just how big an atom is. It's the distance from the nucleus of an atom to the center, to the outermost shell. All right, it's the distance from nucleus to the outermost shell. And the way chemists actually find out the atomic radius for an atom is they actually. So in this case, let's just say this is some atom. Let's just say this is some atom. What they would do is they would take two of the same atom, right? And you would bond it together in a covalent bond. Now, what's going to happen is that you're going to measure essentially the distance between the two nuclei. So this distance right over here. Because guess what? If you take this distance and you divide it by 2, well, you're going to get the distance from the outermost shell to the center of the nucleus, right? So yeah, you just measure this total distance right over here. If you divide that by 2, then you just get the atomic radius. All right. Now, atomic radius, so what you have to know is that, first of all, a group just represents a column in the periodic table, while a period in the periodic table, right, notice how there's a 1, there's a 2, right, it literally says period up right over here. What you have to realize is that a period just represents basically a row in the periodic table. And atomic radius actually increases, so atomic radius increases down a group. So let me actually write this out. So these are the two other periodic trends we're going to look at. I'll do electron affinity in another video. All right, so atomic radius, we could say that this increases down a group. All right, now why is that? Notice how as you go down a group, the atoms pretty much they get bigger. Like literally, look at lithium. Lithium has, this is kind of the electron configuration for lithium. All this is saying is that if you have an atom of lithium, it's going to have 2 electrons in the first shell. It's going to have 2 electrons in the first shell, and it's going to have one electron in the outermost shell. Now, if we take a look at sodium, what this electron configuration is saying is there's 2 electrons in the first shell, hence why there's a 2 here. There's 8 electrons in what the hell? 8 electrons in the second shell. I'm not going to draw all of that out, but you can kind of get the idea. And then there's going to be 1 valence electron. Right, remember, atoms in the same group, they have the same amount of valence electrons, right, in the outermost shell. But notice what is changing. Even though all the atoms have 1 valence electron, notice how as you go down a group, the amount of shells increase. If we take a look at lithium, that has 2 shells. If we take a look at sodium, that has 3 shells, 4 shells, 5 shells. In fact, the amount of shells an atom has matches the period number. Whoa. So the periodic table is pretty cool. All right. Now, literally, as you go down, think about it. If you're adding more shells to atom, the atom's just going to get bigger. Like, it makes logical sense, right? Because adding more shells, atom gets bigger. All right. Now, what happens if you go across a period? So let's say if we were to go from left to right, what happens to the atomic radius? And in fact, what happens to atomic radius is the atomic radius actually decreases across a period. All right. So basically, you'll generally see the biggest atoms, right? If atomic radius decreases across a period and it increases down a group, that means you'll usually see the biggest atoms in the bottom left corner, right? Because across a period from right to left, the atomic radius is going to increase, right? Because if atomic radius from left to right decreases, well, from right to left, atomic radius increases across a period. And if you go down a group, right, this is going to be the overall sort of trend for atomic radius. And diagonally, that's when this area right over here is where you're going to see the biggest atoms. All right. Anyways, let's talk about why the atomic radius decreases across a period when you go from left to right. So let's take the atom of lithium, 2, 1. Okay, so I have 2 electrons in the first shell, 2 electrons in the first shell, and then you have 1 electron in the outermost shell. And it's important to point out that lithium has 3 protons. So this right over here is 3 protons. Now let's take a look at an atom of fluorine, which is in the same period. All right, it's in the same period. So fluorine actually has 2 electrons in the first shell and 7 electrons in the outermost shell. But the thing about fluorine, all right, so 1, 2, 3, 4, 5, 6, 7. But the thing about fluorine is that it's going to have 9 protons. So you kind of see what's happening here, all right? The fluorine has more protons than lithium. So what's going to happen is, remember that opposites attract, right? Positive charges get attracted to these negatively charged electrons. So as a result, these negatively charged electrons will get attracted to the positively charged nucleus. Therefore, it makes the atom a little bit smaller because, well, the electrons want to be close to the nucleus, right? So it's going to, the force from this positive charge is going to pull in the electrons a little bit more than the force from this positive charge, right? Because obviously, in an atom of fluorine, you have more positive charges, a stronger sort of attraction for the electrons than in an atom of lithium. In fact, there's something known as ZeF. All right. Essentially, ZeF, that's going to be equal to, ZeF is equal to atomic, actually, let me just write this down. This is going to be equal to the number of protons. This is going to be the number of protons, and it's going to be minus the number of core electrons. Number of core electrons. A valence electron is an electron in the outermost shell. So a core electron are the electrons that are located, well, they're just the electrons that are not in the valence shell, essentially. They're just the inside shells. So let's see if we can calculate ZeF for an atom of lithium and for an atom of fluorine. So this is fluorine, this is lithium. Let's see if we can calculate the ZeF. And when we calculate it, then I'll tell you kind of what this means. So in this case, we started out with 9 protons, right? We have 9 protons, and the amount of core electrons that we have, that's going to be 1, 2, right? There's going to be 2 electrons in the sort of center, right? I mean, in the core. So that's going to lead to a ZeF value of 7. Now, if we do the same for lithium, that's going to be, so we have 3 protons here for lithium, and there's 2 core electrons here. 3 minus 2 is equal to 1. So the ZeF for lithium, that's going to be equal to 1, and the ZeF for fluorine, that's going to be 7. All this is, now this kind of means is that the valence electrons, all right, so let's start out with lithium actually. So what this 1 basically represents is that this electron, this valence electron right over here, feels a force of attraction of 1 proton to the nucleus. And you might be asking yourselves, why is that, right? Why do valence electrons only feel such a weak force of attraction, right? Isn't there 3 protons, right? There's 3 protons in the nucleus. So why is it that the valence electron only feels a force of attraction of 1 proton? And the reason why is because these core electrons are cock blocking the valence electron from the nucleus, right? Think about it. These electrons constantly move around this atom, right? They are cock blocking this valence electron from feeling that force of attraction to the nucleus. So because of this blocking, well, or electron shielding, as it's also called, right? I spelled it wrong, but these electrons basically just shield this force of attraction or block this force of attraction for this atom right over here. So this valence electron is not feeling that strong of a force of attraction to the nucleus. Meanwhile, if we look at an atom of fluorine, notice how the ZeF value is 7, meaning that the valence electrons in fluorine feel a force of attraction of 7 protons to the nucleus. It feels a force of attraction of 7 protons. And 7 is way stronger. 7 protons is a way stronger attraction than 1 proton. So that kind of supports our idea that the more protons in the nucleus that you have, the more the electrons will be attracted to it, right? Notice how in the same period, right? Notice how as you go from left to right in a period, notice how the amount of core electrons does not change. And because the core electrons does not change, and the thing that does change is the amount of protons that you have, that's going to lead to a higher ZeF value or a higher sort of attraction for the electrons to the nucleus, right? The amount of cock blockers you have stay the same, but the amount of attractors you have increase as you go across a period. So, you know, if you got more attractors, hey, that's going to lead you to a smaller nucleus. All right, let's talk about ionization. Not a smaller nucleus. What the hell is that? It's a smaller atomic radius. All right, let's talk about ionization energy. Ionization energy is just the energy required to take an electron off an atom. Ionization energy is always positive. It's always going to take energy, right? It's going to take some energy in order to take an electron off an atom. Okay. Now the thing about chemistry is that it likes to build off of previous concepts. So let's use the idea of atomic radius in order to explain ionization energy. So let's talk about ionization energy down a group. All right, so do you think ionization energy increases or decreases down a group? All right, and I want you to like really think about this. All right, based on what we said about atomic radius, right? We said how atomic radius increases down a group. So how do you think ionization energy will change if you go down a group? Well, think about it. The atoms are getting bigger, all right? The atoms are getting bigger as you go down a group, right? Let me just do like something like this, all right? So therefore, notice how when the atom gets bigger, well, the electrons are further away from the nucleus. Therefore, it's actually going to take less energy for you to pull this electron out, right? Ionization energy, maybe I should have specified this, but remember, it's the amount of energy it takes to remove an electron from an atom. And the thing to know is that it's from the outermost shell. From the outermost shell. All right, so you're trying to see how much energy does it take to move an electron from the outermost shell. Well, if atoms get bigger, the electrons on the outermost shell, the electrons are going to be further away, right? The electrons in the outermost shell is going to be further away from the nucleus, and therefore it's actually going to take less energy in order to remove that electron. All right, now some of you guys might be thinking, but the problem is that if an atom gets bigger, well, it's also going to have more protons. So won't that attract the electron more, and the distance and this charge kind of balances out, so the ionization energy will be equal, right? Because even though the electron, if an atom gets bigger, right, the electron is going to be further away from the nucleus. But you might argue that, well, so the amount of protons is increasing, right? Even though the electron's further away, we still have more protons than we did with the smaller atom. So how does that make a difference? And this is when something known as Coulomb's law. Coulomb's law explains this. All right, Coulomb's law explains this difference. Coulomb's law basically explains that the force of attraction between sort of two particles, right, that's going to be proportional to the charge of those particles. But the problem is that, like, as distance increases, the force actually gets weaker. Okay, so it's going to be inversely proportional to the distance. Let's just do a quick example so you guys can kind of see. Let's say if we have something with a 2+ charge, and let's say if we have something with a 2- charge, they're going to have a stronger force of attraction than if you have something with a 1- charge and a 1+ charge, assuming that distance is going to be equal, right? If we're assuming that the distances between the things are equal, if the higher the charge, right, the higher kind of the charges, right, the greater the charge is for two particles, well, the stronger the force of attraction. It also kind of says that, well, think about it. This kind of just makes logical sense. But if you have two charged particles, let's say these two charged particles are pretty close to each other. However, if you increase the distance between these two charged particles, the force of attraction is going to significantly weaken. In fact, it weakens so much that it's distance squared in the denominator. So even a tiny change in the distance, that value is going to be squared. So it's going to have an even bigger impact on the force of attraction, right? Think about two magnets, right? If you have two magnets, if you place two magnets together really closely, it's going to stick, right? It's going to stick to each other. As soon as you move it away a little bit, then it becomes super, super weak. You can barely even feel it. So distance plays a huge role in the force of attraction. And the thing is that the distance actually between the two particles, between the nucleus and the electron, actually outweighs the effect of basically a bigger nucleus with more protons. All right, distance plays more of an effect on the amount of charge. Remember that. Remember Coulomb's law. Distance has more of an effect than basically the amount of charge, right? Whether it's a 2+ or a 3+, whatever. Distance triumphs that. All right. So yeah, this is why ionization energy decreases down a group, because atoms, they get bigger. Distance from the valence electron to the nucleus, that's going to increase. Therefore, the electron does not feel as strong of a force of attraction to the nucleus, so it's easier to pull it off. Now, ionization energy actually increases across a period. So ionization energy, if you want to find something with the highest ionization energy, you would have to go to the top right of the periodic table, right? If atomic radius decreases down if ionization energy decreases down a group, That means that if you go up a group, ionization energy will increase. And it turns out ionization energy increases across a period from left to right. So in this top corner right over here, you will see the atoms with the highest ionization energy. Now, why does ionization energy increase across a period? Well, we can use our prior knowledge about atomic radius to answer our question. Remember that atomic radius decreases across a period because guess what? Across a period, there's going to be more protons. So the electrons are going to be more tightly bound to the nucleus, right? It's going to pull it in a little bit more. So if the electrons are more tightly bound to the nucleus, it's going to take more energy to pull them off. Boom. All right. So you use the atomic radius kind of information to answer your ionization question, right? The electrons are more tightly bound to the nucleus. Therefore, it'll take more energy in order to pull that valence electron off. Let's take a look at electronegativity. All right. Electronegativity refers to how well an atom attracts electrons. Let me see, how well an atom attracts electrons in a chemical bond. So when an atom is bonded to another atom, how well does that atom attract electrons? It turns out that electronegativity follows the same trend as ionization energy. So electronegativity actually decreases down a group and increases across a period. But an important thing to know about electronegativity is that remember that noble gases have an electronegativity value of 0. So look, electronegativity is sort of like a value that you can sort of measure, which tells you basically how well an atom attracts electrons in a chemical bond. And essentially, remember that it follows the same trend as ionization energy, but most importantly, electronegativity caps out at 4. All right, a value of 4. That's the highest electronegativity value. The highest value goes to fluorine. All right, fluorine gets the award for the highest value of the electronegativity, 4. Noble gases have electronegativity value of 0. Noble gases, they're stable. They have 8 valence electrons. They don't want to react, right? So in a chemical bond, they don't want to attract electrons because they're kind of happy the way they are, if you know what I mean. However, remember that atoms like xenon, which is a noble gas, xenon is noble gas, they do sometimes form chemical compounds. So like noble gases, most of the time they don't want to react, and like most of them, they have an electronegativity value that's 0, or something that's close to 0, right? That's basically the general rule. Sometimes they can react though, so that's just like the thing you got to watch out for. There's always like exceptions, all right? But that's in general. Okay, noble gases, electronegativity value close to 0. Okay, now let's see. Electronegativity decreases down a group. Can you explain why? Well, let's say that if we have a very big atom, all right, a very big atom that's very low on a group. So if I were to choose like an atom that's very low on a group, right, it's going to look something like this. It's going to have many shells, but to simplify this, let's just say this is a very big atom. And let's say if it's bonded, let's just say if it's bonded to another atom. I know this is going to be a little bit cursed, but trust, all right. Let's just say this is bonded to another atom. Now, because the nucleus is so far away from the other atom's electrons, well, guess what? It's not going to be able to attract the electrons that well. Meanwhile, if you have a smaller atom that's bonded, to another atom, well, guess what? The nucleus is closer, so it's more able to attract the electrons. All right? You're using the atomic radius as basically the proof for all of this, okay? So it decreases down a group. Electronegativity increases across a period because guess what? Across a period, you have more protons, right? You have a smaller nucleus, so therefore, the electronegativity increases across a period. As if you have more protons, well, guess what? You're gonna attract better. All right, that's just the reality. Now, yeah, that's pretty much it for all of these. If you know what I'm saying. So yeah. In addition, we also got to know cations and anions. So be wary of this. Cations and anions. Remember that cations are positive, right? So let's say if you have an Na atom, and actually one more thing about electronegativity, it kind of makes sense why electronegativity also increases across a period. Another way you can think about this is think about metals, right? Metals, they want to give away electrons. So they don't want to attract electrons in the first place, right? how well an atom attracts electrons in the first place, metals are like, nah, bro, we're not even trying to attract them in the first place. We're going to have a low electronegativity value. Meanwhile, non-metals, right, a lot of them, they want to gain electrons. So it makes sense why they would have a higher electronegativity value. Anyways, cations, let's just say Na, right? These are usually metals, right? We have metals, Na turns into an Na plus ion. AKA it loses an electron. Because an electron is negatively charged. If you lose a negative charge, you're becoming more positive. Now, what do you think the atomic radius? How do you think the atomic radius will change if something becomes a cation? So let's say if this is an atom of sodium, right? Let's just say this is an atom of sodium to simplify things. How do you think the sodium ion will look like? Will it be bigger or will it be smaller? Now, the thing about sodium has an electron configuration of 281, meaning that 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the third shell. Now, when Na loses this valence electron, let's say if sodium loses this valence electron, well, what's going to happen? Sodium is actually going to lose the entire shell. So this entire shell will pretty much be lost because, well, sodium lost the valence electron. So now, yeah, right, this is the only valence electron that it had. You lose it, now you pretty much just lost the shell, and the stuff from the second ring pretty much become the new valence electrons, right? So cations are actually smaller than their original thing, right? Cations are actually going to be smaller than what they were originally because, well, you're losing electrons, right? If you're losing electrons, you're going to be essentially losing a shell, an entire shell, and that's gonna lead to a smaller atomic radius. Now, anions are the opposite. When you have an anion, let's just do something simple. Let's say fluorine, 2, 7, all right? So 2 electrons in the first shell, 7 electrons in the second shell. When fluorine gains an electron, it's going to become the fluoride ion, okay? Now, do you think fluorine, when it gains an electron, right, or, anions, right, when something becomes an anion, the atomic radius increases. The reason why? Well, originally fluorine had 7 electrons in the second shell. 7 electrons. 1, 2, 3, 4, 5, 6, 7. When it gained an electron, now it has 8 electrons in the outermost shell, right? 1, 2, 3, 4, 5, 6, 7, 8. Notice how I had to make my circle bigger because there were more electrons, right? It's like your friends, let's say if you're at like the lunch table, right? It's looking a little bit full in the lunch table, but another friend decides to come over and sit with y'all. So what do you got to do? Y'all got to make room for that friend. All right. Now, if you take a look at this example right over here, notice what the electrons are doing. The electrons are pretty much just making room for this extra electron. And in addition, the electrons, right? Remember that opposite charges attract, right? So the electrons attracted to the nucleus, but remember that same charges repel each other, right? Like charges repel each other. If opposites attract, like charges repel. So in this case, right, if the electron is introduced into the atom, well, that's going to repel the electrons. Right? The electrons do not want to be close to each other. So they're, in addition to that, they're going to make space for this new electron, essentially, right? And this is something known as electron repulsion. I'll just write it like this: electron repulsion. All right. The electrons do not want to be close to each other. So when you introduce a new electron into the atom, they are going to be making room for that new electron because they just do not want to be close to it, right? They got to make room for that. So yeah, that's pretty much it. Cations, smaller, anions, you get bigger than the original. All right, so one final thing about ionization energy. Let's say if we're looking at an atom of sodium. So this is an atom of sodium. Remember, it's 1 valence electron here, and then these are the core electrons. 1, 2, 3, 4, 5, 6, 7, 8. And then there's 2 core electrons here. Now, you can have multiple ionization energies. So essentially, look, the first ionization energy is basically the amount of energy it takes to remove this electron right over here, the outermost electron. But there's also something known as the second ionization energy. Essentially, how much energy does it take for you to remove an electron after this electron has been removed? So after this electron has been removed and this atom right over here becomes an ion, how much does it take to remove another electron? Now, the thing is that once you remove the first electron, let's kind of see what happens. So an atom of sodium, remember, an atom of sodium has 11 protons. And once again, we're going to use this idea of Zeph, okay? This idea of Zeph in order to kind of see what happens. So when we remove when we look at this electron right over here, this valence electron, remember that in order to calculate Zeph, or the effective nuclear charge for this electron, what you do is you take the amount of protons you have and you subtract it by the amount of core electrons that you have. So the Zeph for this electron in this case is 3, meaning that this electron feels a force of attraction of 3 protons to the nucleus. So for the first ionization energy, let's say we remove it, all right? Let's say if we remove this electron. So we're just going to be left with all this random stuff. All right. Now let's tap into the second ionization energy, if you know what I'm saying. So we've got the second ionization energy. Let's say if we're trying to remove this electron. Now for this electron right over here, let's calculate the Zeph for this second electron. So the Zeph in this case, well, we have 11 protons in total. And now, guess what? Now there's only 2 core electrons. Because guess what? You just completely removed a shell from the atom, right? So what's going to happen is that now the second shell basically becomes the new valence shell. So essentially, now you only have 2 core electrons that shield the nucleus from this force of attraction. And you actually get that the new Zeph is now 9. So guess what? This electron feels a force of attraction of 9 protons, right? And so the second ionization energy is going to be greater than the first ionization energy. Because guess what, right? When you're like in the first group for the periodic table and first group for the periodic table, and you remove an electron, well, what that does is now you got to tap into the core electrons. Right now you're dealing with the core electrons, which are, or basically, no, there's less, sorry. Once you have removed the outer shell, well, now you're going to be dealing with less sort of blockage, right? Now there's going to be less core electrons to sort of block the nucleus, right, from the attraction of the electron, meaning that there's going to be a stronger attraction from the nucleus to from the proton to the electron. Therefore, the second ionization energy is going to be greater than the first ionization energy. Now, let's say if we were to look at an atom of, let's say, calcium, or actually to be a little bit simple, let's take a look at beryllium. So beryllium looks something like this. So you have 2 electrons here, and then you have 2 electrons in this shell right over here. Now the first ionization energy, right? It's going to take some strength to pull away this first electron. All right. The second ionization energy, it's going to take a little bit more strength. It's going to take a little bit more energy in order to pull away a second electron. All right. So think about it like this. Why does this happen? So if we were to have the first ionization energy, which takes away this electron right over here, why is the second ionization energy still greater than the first ionization energy? Why is that the case? Because in this case, right, we're dealing with beryllium, and when we take an electron away from beryllium, we still have 1 electron left, right? We still haven't lost a shell. In the sodium example, we have lost a shell, and that's what makes the second ionization energy actually much, much greater than the first ionization energy. But in this case, the second ionization energy is still greater than the first ionization energy somehow, even though we didn't lose a shell. So how can that be the case? Well, the thing is that when you lose a negative charge, you're becoming more positive. And positive, remember, opposites attract, right? So it just turns out that cations, when something turns into a cation, right, it's actually going to be harder to remove another valence electron than if you were to remove it from just like a neutral atom of that type, in this case magnesium. So remember that the second ionization energy is going to be always greater than the first ionization energy. However, if we were to actually, so after we take away the second shell, if by chance we were to actually know the value for the third ionization energy, well, then you'll find out that it's going to be much, much, much greater than the second or the first ionization energy. All right. Remember that when you're removing electrons, but you're keeping the valence shell, the ionization energy is only going to be, it's going to be slightly bigger than the first ionization energy. But when you start tapping into the core electrons, that's when the ionization energy becomes way bigger, because then you're dealing with the core electrons. The Zeph value completely changes, and you're going to get a way stronger force of attraction between the nucleus and the outermost electron. All right, so let's take a look at an example. So if we have these different ionization energies, so let's say if we have ionization energy 1, that's 580, then it increases, right? Because remember that the more ionization energies you basically have, right, the more electrons you remove, right, the harder it is to remove. Now notice how there's a big, big jump between number 3 and 4. And this tells us that this is like a scenario where, like we were dealing with sodium, right? When we were removing one of the outermost electrons and we started removing the inner electrons, then, the ionization energy started increasing drastically. So when we're dealing with this problem, we can actually say that this element is in group 3A and that it has 3 valence electrons. Because the thing is, look at ionization energies 1, 2, and 3. They are relatively low compared to the ionization energies of 4 and 5. So therefore, right, this element has to be in group 3, because these 3 ionization energies represent me removing a valence electron, from right. But then when we start to get to ionization energies 4 and 5, then these represent me sort of removing the former core electrons. So these represent, the core electrons essentially, right? We're trying to remove the inner, more core electrons. The valence electrons, they're always going to take less ionization energy to remove than the core electrons. So if you see a big jump, that tells you, oh, we've gone to the core electrons. So everything above what we have originally counts as a valence electron. Everything basically below it counts as the core electron.